Hi all. Um Here today in this video tutorial we are going to see how we can make an op amp, how we can use an op amp for the simulation of a summer circuit, simple summer circuit. Here we are going to create our summer circuit in gEDA. It's a GPL, electronic development automation software. So for that, create a folder with a name summer or something, as your choice. So here I am going to create a file like summer.sch, where sch is extension of sch means something schematic, and which is extension of gEDA schematic editor. So right click on the file and open with the gEDA schematic editor. Okay, now now we have to import our components to the editor. So for that, we have an option called art. In art we have a menu which is component. While we clicking the component, we will get a dialog box like this. In this we can specify, or we can write whatever component we need in our circuit. So as we know, our primary target is a summer, so we must need an op amp. So first we'll go for an op amp. Just type it here. Okay, this plays if you while we're typing here, this simulator, we will get some similar components like here. So while we if we click any of the menus or any of the components listed, we can see the image of the component. So here we are going to take this op amp. So just click art here. I will just zoom it so that we can see it clearly. Okay, now I got an op amp. So okay, no, I just want to change the name. Okay, whatever maybe the name, just give some value. Now we have to import some another components. As we see here, there's a there's a shortcut I for importing the components. So we will just press I. Now we got some. Now we need some resistors and all resistors. So just type it so we can see whatever resistors are here. So we'll just import what we needed. So for a summer, we need at least 3 resistors. For that purpose, because we have to for 2 resistors for summing, and one resistor is a feedback resistor, which is very important in the case of operational amplifiers, because the feedback resistors produces gain for the op amp. Now we have to join these connections. So for that we can use net. Here is an option for net. So after clicking that option, we can go through whatever joins we have to make. Click between 2 terminals, so that a wire connection that will come, and now we will join all these things. So simple to connect all these things. So here I got missed a connection. Okay, I'm sorry. So before we have to, it's better to change the name of resistors. It's already rough dust, that reference value. So it's better to change whenever we import all these things, so that it will be easier for us. So it's RF means feedback resistor. So for our op amp, we are actually grounding the non-inverting terminal. No, for simple purposes, it's enough. Okay, for that we will import another module which is ground. Yes, we will ground, play somewhere like somewhere here. So we will create a netlist, and here we have to give a connection from here to the non-inverting terminal to these node of these resistors. And now we will import VCC for the op amp. We have got VCC and minus VCC which can be used. So you see, so we can specify the values for VCC. So for that, double click on the model and now give value. There is an option value in the name, so give some value like 15 volt as we usually do. Show value only, okay, so, and give the option add. Similarly, we can give it for minus VCC, so this 15 volt, and we will select value only. Okay, fine. Okay, now you have to add two signal sources. These are signal sources, no, it's voltage sources. It's actually, it's like voltage sources here. So what we are going to do is we are going to add a transient source and a DC source. And we will see what we can see, what we observe. To rotate, no, actually we have to come. We need the positive near the other, so we are going to rotate the source, and we will provide some name. So let's say V1, V2, and we need two ground points. It places here. Okay, now it's time that we can add values to resistors, and we can create some net files. Okay, first of all we will go for net. We'll add some net values so that we can plot it later and we can verify while we simulating it in a spice. Say N1 and N2 be here, and okay, let's something be we will give a name N0 for output. We can verify. We will assign ground potentials here. We'll give some value 0. It's not that much necessary. Fine with that. Okay, now it's time. Okay, we'll place a load resistor here so that we can observe the output across the load resistor. Smooth operation, we can rotate this, place it. Okay, so we'll copy a ground using normal control C, control V options, normal cut and paste options. Here let's say R3. Okay, now it's the time we can add values according to our specification. So for that, let's say we are giving a 5 kilo ohm resistor. For that, go to it's 5 kilo ohm. Okay, here we go, some 10 kilo ohm. See. And for the source resistors, we will give something like actually we are expecting a 10 gain, so that we can it's while doing a simple maths, so 10 by 1, it's 1. So actually we are placing a 1 kilo ohm resistor for both the sources. Okay, now we will go for sources. We can assign a value for sine voltage source as sine, in the bracket this is a starting value, and there's a peak to peak value, and we need 1 millivolt on plus we need a peak to peak value between plus 1 and minus 1 volt, and we are specifying the frequency of operation. That's say 50 kilohertz. Okay, and start it. And for this it's a simple DC source, so we just give 1 millivolt or something. Okay, now it's the time, so it's the time we are going to choose value for our op amp. I will just start assign 0 to this ground 2, and this that name is okay. Actually we are going to use OP07 model for this op amp, so we have the model file for it. You can download this from the link given with the video. So here I got a I have already saved this file in the folder of the summer.sch file. Okay, here we have this file, so we are generating a spice model for this file. So for that we will go to the circuit and we will insert another component. This is a spice model. Just type the spice model. So we got a spice model type, so we are adding a spice model here. Some name, let's say A1, and the model name what we need is OP07. so OP07. Okay, the OP07 can be found out from the subcircuit of this OP07.gEDA, because here we have a subcircuit OP07, and we are using this subcircuit OP07 for our purpose. Here we can say this 32746, just as similar to our pins, no, our normal pins here. Okay, now we will specify the file where the file is located. So here it's in current directory op07.cir, small letter cir. So here we got the dot slash indicates the current directory, the current working directory. We got this file located in our current working directory, which is here we got it. Now we will add this model to our op amp, so that we can replace this model, replace this op amp with while we creating an netlist, we can replace this op amp with that model, that corresponding model values. So we'll just add this value, C OP07 caps. Okay, I think now circuit is almost over. Just add 0 to, okay, it's already added. And okay, now we are almost done, so let's simulate this. Okay, I will change this frequency to 10 kilohertz, so it will be easier for us to simulate. So for simulation, go to the folder that we created, our summer.sch file. So create open a terminal in that directory, and now you have to generate our netlist. So there is a command called gnetlist space minus g, and there is an arguments minus g spice minus sdb space minus o, our output file name. Let's take summer.net and our input file name summer.sh. So it executed successfully, and we got a summer.net file which includes all our models and our connection details. So okay, now we will simulate, we will try to simulate this summer circuit. So for that, just type ngSpice. So since we are using ngSpice to simulate our netlist, now source netlist that we created summer.net. So for that, type the command summer.net. So it's actually the summer file gets sourced. So we got some warnings. Let's ignore this. Some photos. So now we are going to deal with the transient analysis. So we will take the trans. So for that, we have got a command tran, and we have to specify the steps. For that, it's let's say 0.1 millisecond, and the number, I mean the end, we have to specify, let's say 0.4 millisecond. So it's simulated, so we got all variables like here. So number of rows, I think it's executed successfully. So we'll try to plot our values. We have got n1 here, so it's 0. It's a sine wave between -1 and 1 millivolt. So we'll plot n1. Yes, here we got a model. So it's almost like a sine wave, which varies between 1 millivolt. So we will now go for what will be our n2. Yes, we have actually placed our net name n2 before a DC voltage source. So we got a DC voltage level is 1 volt. So now we will move to our expected output. Further, once again go to the terminal. So here, okay, now we will plot out a value n0. So which is our output net name. Plot n0. So command. Yes, now we got a sine wave which is shifted. Which is shifted -10 millivolt downward. We'll see. We got a 1 millivolt plus this 1 millivolt DC, 1 millivolt sine wave plus 1 millivolt DC. So it will be added up to a sine wave of which is shifted 2 millivolt, which is shifted to 1 millivolt. And we are giving that value to an op-amp with a gain -10. So when we give a -10 value here, so the whole thing is multiplied by -10. So we'll get a value between our value which was between 0 to 2, which will be multiplied with the -10. So it will now it will vary with 0 to 20. So we got a correct output, and our spice model is done. Okay, now in the next video we will see how to generate PCB layout for this circuit. Thank you.